So I want to thank the organizers for inviting me back for a second trip this semester. So like all of you, I think that a lot of the most interesting things happening both in computer science and in physics right now are at this interface. So I also think that, we've all seen proofs that consist mostly just of controlling error terms and dotting T's and crossing I's and certifying things that we already knew were true. And then we've seen other proofs that really seem to illuminate why things are true. So in other words, proofs not merely as certificates of truth, but as one of the instruments we use to figure out what the truth is. And I think one reason why I like this field is I think most of the proofs we see are in the second category. Okay, so this, I'm going to present joint work with Jess Banks, who you should be overjoyed to know is joining the math department here this fall as a graduate student, and Joe Neiman and Pranith Netrapalli. If I have time at the end, I will also show some work with Jess and Roman Vershinin and Jiaming Xu. And, but a lot of this has grown out of this larger collaboration that Florent told us about this morning with him and Lenka and a sort of cast of thousands who've been working on the clustering problem. So also Caterina Di Bacco, their student Thibault Lesieur, Jess again, and with lots of good advice from other people. So, so first of all, I want to redraw that picture that we saw a couple of times this morning, and where first you have a lot of solutions, and then the solutions break up into clusters.
Colors.
Oh, yeah, okay, well that helped wake you up. And so then there's this position called condensation we heard about. And above here, as we heard from Alan and Nike, at this point, one of these clusters kind of dominates. Things become sort of more chaotic at that point because what matters is the few largest clusters rather than a typical one. And then in constraint satisfaction problems, then we hit the satisfiability transition at some point, and everything disappears. But in planted problems, something else happens because there is actually a planted solution which was built into the problem from the beginning. And so this is our situation in statistical inference, where we assume that where did this problem, this graph, or this data set, or whatever it is, come from? Well, we assume there's some planted model where there is some underlying ground truth or some underlying signal which we're trying to discover. So in the community detection problem, it would be a partition of the vertices into communities. In the clustering problem, it would be a partition of the points into clusters, with maybe also information about where the clusters are. And we observe that through some noisy channel. So here, and we heard about this earlier today, on this side of the problem, things are so concentrated around that true solution that the problem becomes very easy to see where it is. But down here, you can't actually tell what the planted solution was. And in fact, you can't even tell the difference between this distribution and a null model where there is no underlying signal at all. And so this thing here is, this conjectured computational threshold above which some spectral method or belief propagation or something like that can hopefully be proved to work. But then there's this information-theoretic threshold that we also heard about from Florent, and that's the same as condensation. Okay, so the idea is that to the left of this line, well, it's true you have all these clusters. One of those clusters corresponds to the ground truth, but actually all the clusters look pretty much the same as each other, and even if I showed them all to you, you would have no ability to tell which one corresponds to the ground truth. Whereas to the right of this line, you can really tell because this cluster will actually be, for instance, bigger in the planted model than in the null model. And we saw a graph of this in Alan's talk, for instance, where the free energy below this point is the same in the two models, and above that point there's a higher free energy in the planted model because there are more solutions, because there is a solution built into the problem. All right, so good. So now, to make all this more concrete, let me remind you of some of these models, which some of you know very well, but for the folks at home on YouTube. So let's talk about the stochastic block model. So this goes back to the 1980s in the sociology community. It was rediscovered multiple times. Some people call it the inhomogeneous random graph. And in computer science, it's popular to call it the planted partition model. So we have n vertices, and we have k types of vertices, or groups, or communities, or blocks. And I will work in the regime where k is order 1. And then there is some k by k matrix telling us the probability that a given pair of vertices of this type and that type are connected. And I'm going to be working in the sparse regime where this probability is C sub the type of U, sorry about the double subscript, comma the type of V over n, where C is this k by k matrix. A very popular special case is where C sub rs is C in if r equals s, and C out if r is different from s. So one probability for connecting with others in the same group as you, another typically lower probability for connecting to people in the other group. And so this labeling here, which is this map from the set of vertices to the set of types, is the ground truth that we're trying to discover in this case. So the game is that someone, nature or God, chooses this labeling, then generates the graph according to this model, then shows you just the graph without any of the labels. There are many other games we can play. We can show you some of the labels and so on. I will focus on the case where, for some reason, we do actually know these parameters. Learning those parameters is another interesting problem. I'll assume that you know the number of groups, ditto. And then your goal is to label those nodes and to come up with a something which gets as many labels correct as possible. So we can imagine various priors, but let's assume that the labelings are all equally likely. So then this is the total probability of seeing a certain graph, which is there called capital X, but maybe later I'll call it G. All right. So the null model here that we would like to distinguish from is where we just have an Erdős-Rényi graph. So Q of G would just be Erdős-Rényi, where C in equals C out, and where there really are no communities at all. So while we're at it, let's just write down the average degree. So the total number of neighbors you have in the whole world in expectation. And now I also really like parameterizing sort of the strength of the community structure in the following way. I will call lambda C in minus C out divided by k times the average degree. And why do I like putting it that way? Well, if you take this matrix, which has C in on the diagonal and C out off the diagonal, and you add up the columns, you get this, which is k times the average degree. So if we divide by k times the average degree, we get a doubly stochastic matrix. And with this value of lambda, this doubly stochastic matrix is lambda times the identity plus 1 minus lambda times the flat matrix. I like to call the matrix of all ones capital J. So this is the matrix where everything is 1 over k. So another way to put this is, if I'm in a given group and I don't tell you anything else besides the fact that you and I are connected, then this is the transition matrix for telling you the probability distribution of your groups. Lambda is the probability that you're in the same group as me. And then 1 minus lambda is the probability that you're completely independent of me. So it's sort of the probability that information gets transmitted along that noisy channel. I should mention that, one special case of this that some of us have thought about is the planted coloring problem, where you're completely not allowed to connect to others in the same group. So Cn equals 0. And in that case, lambda is minus 1 over k minus 1. So it's negative. Things are disassortative or heterophilic or antiferromagnetic, as opposed to assortative or homophilic or ferromagnetic. Okay. Let's learn some new words. Okay. All right. So again, there are these two basic problems. So one is what you might call the detection problem, although a more traditional name for it would be a hypothesis testing problem. So, which is tell whether the graph G is drawn from P or Q. So tell me whether there are actually any communities. And then we could also talk about what is variously called the reconstruction or recovery problem, or I'm sure it has other names too, which is find that labeling. Now, when computer scientists and lots of other people first see this, the typical reaction is to say, oh, I want the maximum likelihood estimator, sigma hat, which would be the one which maximizes the probability of getting that graph. Or if there's a parameter, we would call it the, I wish I didn't know what this stood for, maximum a posteriori. This is one of these acronym-laden fields. And when things are reasonably dense, like an average degree, which is growing logarithmically in n, this is a fine idea. And in fact, people like Bickel and Chen and lots of other people, including more recent work by Abe, Bandaira, and Hall, have shown that in certain regimes you can label everyone correctly. But in the really sparse case where the average degree is order 1, this is a bad idea. Bad, bad, bad. So you just don't actually want to view this inference problem in this naive way as an optimization problem. And I learned this from Lenk and Florent. You really need to care about the entire posterior distribution of the labeling given the graph. And for instance, if you want to maximize the number of nodes labeled correctly, you want to compute the marginals of this distribution and not just find the most likely case. So, let's say that I give you magical access to that entire distribution. We're going to throw computational complexity to the winds. The question then is, how much does that distribution tell you about the ground truth? So it could be that that distribution looks like this, and that the ground truth is just one of many, local optima. It might not even be a local optima. And you would have no way of telling which one it is. That would be like this situation where, yes, there are clusters, but all the clusters look equally good. Or it could be that it looks more like this. Sure, it might be bumpy, but there's some correlation between a typical draw from the posterior and the ground truth. And so if you like, we're trying to prove upper and lower bounds on that information-theoretic threshold or if you prefer the physics term, on the condensation threshold. All right. How are we going to do this? So I'm going to focus on showing bounds on when we can do detection. It is intuitive that if you can't tell the difference between the stochastic block model and an Erdős-Rényi graph, that if you can't tell whether communities exist, that you also can't label them better than chance. However, our proofs that that the latter follows from the former are not as generic as we might like, and in fact, you can come up with silly, trivial cases where you can't tell the difference between the planted model and the null model, but if I promise you that the data is drawn from the planted model, then you can tell the ground truth really easily. So the connection here is not totally as clear as we would like, I'll focus on the detection problem. All right. So our main tool is going to be the second moment method. The second moment method rides again. All right, so what are we going to do? Well, given the graph, there's what people call the likelihood ratio. So there's the probability of that graph, and there's the probability of getting that same graph in the null model. And, so what do statisticians do all the time, at least some of them? I forget whether this is the Protestants or the Catholics in statistics. That's a little joke. But you can do this thing called likelihood ratio testing, where you would look at some threshold. So the question, intuitively though, if this ratio isn't actually very big or very small very often, then it's hard to tell these two things apart. And so indeed what we're going to do is bound how much this ratio varies. So we're going to look at its expectation in the case where the graph is drawn from the planted model, which if you think about it is also its second moment when it's drawn from the null model, because both of these are just the sum over all graphs of p squared over q. Okay. So why is this enough to tell us anything? Well, I think one nice reason is to look at the Kullback-Leibler divergence between the two. So this is the average of this ratio, of the log of this ratio, and by Jensen's inequality, this is less than or equal to the log of the average, which is the same thing. So if this is order 1, then this whole thing is order 1, which means that if I drew the graph from the planted model where there really are communities versus the null model where there aren't, there would only be a constant number of bits of, that's interesting. And intuitively, with only a constant number of bits, it would be hard to get order n bits out of it and do and get the labels. But the other reason why this is interesting is this notion of contiguity. So if we have two families of probability distributions on objects of size n, then we write this. If you have a family of events called E, if the probability of those in the null model, Q, is tending to 0 as n goes to infinity, contiguity means that it also goes to 0 in P. So for instance, if you had a community detection algorithm, if it never says yes in the null model, it must also never say yes in the planted model, which means that it can't get both things right with probability tending to 1. Okay. Now, what you would really like to do is show that this works going in both directions. That takes more work. So Massel, Neiman, and Sly did that. And I should mention, I should mention that also Joe and Praneeth did that in a preprint, which became one half of this combined paper. So with the small subgraph conditioning method, you can really explain away a lot of the variance and reveal that, really gain insight into the structure of this distribution, and then reveal that in fact, this ratio is with high probability finite, as in bounded below infinity and above zero with high probability. And then you have both directions. So I'm just going to focus on one direction. Even though they were able to show for the block model that whenever this second moment bound holds, then that bidirectional contiguity holds as well. All right. If you've never seen this notion before, notice that it is a much, much weaker notion than saying that these two distributions are close in L1 distance, or total variation distance. Indeed, it could well be that the null model looks like this and the planted model looks like that, or something like that. It's perfectly fine if a given graph is twice as likely or half as likely in one model as the other. So they could be quite far apart in variation distance, but it's just that this ratio, roughly speaking, has to not go to zero or infinity. All right. So let me briefly show you the proof that if the second moment is bounded, then this holds. It's just Cauchy-Schwarz. So P of E is just this sum, P of G, the indicator random variable for E, and let's rewrite that as the sum over Q of P over Q times that indicator random variable. And then using Cauchy-Schwarz, this is less than or equal to the square root of the sum of Q times P over Q squared, which is our second moment, times the sum over Q of the indicator random variable squared, which is the same thing, and this is Q of E. So if the second moment is bounded and Q of E is tending to zero, then P of E must also tend to zero. So, and I don't know, I just want to, I have to give Charles Bordenov credit for showing us how simple this was. He did that at a nice tutorial at a workshop in Santa Fe last December. All right. So now we can just try to bound the second moment. But we get to have lots of fun doing that. There's some optimization problem here about keeping the population of markers balanced between the two trays. It's like those city bike rental programs. Okay. All right. Let's see. Is there anything else vital I wanted to say? Oh, I just erased some of the useful. Oh, no, there it is. Okay. All right. Tum. Good. So, again, what are we computing? We're computing the expectation when the graph is just an Erdős-Rényi graph, when it's drawn according to the null model, of the square of the expectation of the graph in the planted model, given given some ground truth, which we don't know, times this. And so expanding this out and reversing the order of the expectations, we can write this as the expectation over all pairs of partitions, and then the expectation over the graph of P of G given that versus given that. Okay, that doesn't go any further. All right, good. So let's expand this out a little bit more. So all of these probabilities are just products over all the edges. So maybe it's worth writing down over here that the probability of G given a partition is just the product over the edges of of the probability that those edges are there times the probability over the non-edges of the probability that they're not. Lots of you have seen this before. Good. So then what do we get here? We get the product over all of the edges of the expectation of either C sub sigma u, sigma v, C sub tau u, tau v over C squared. That's if there is an edge between them, versus 1 minus this one with the sigmas, 1 minus this one with the taus, and then 1 minus C squared. And that's if they're not. Okay. So I'll let you do the next line or two, but when n is large, of course we can turn, so since these are all independent, this is a product, and then we can turn that into an exponential of a sum. And it will depend on how much sigma and tau have in common, as always. So let us define an overlap matrix. So I'll say zeta sub rs is the number of vertices which are in group R according to sigma and in group S according to tau. If I divide by n over k, then if I assume for simplicity that the partitions are balanced with n over k vertices in each group, which is not a big deal, then this is a doubly stochastic matrix. And then when I plug that in here, can I write on that? No, I can't.
If you're the first, you can do that.
What?
Only if you're the first. Then
Oh, good. Yes. All right. It's the erasing that's the problem. Good. Okay.
Cris. Yes.
I think Alistair would be mad at me. Okay. Anyway, the punchline is that by summing, we can sum over. Let's see. Well. So this will be the expectation over these pairs of partitions of e to the lambda squared, where that's this eigenvalue of the parameter matrix, the block model, times the average degree times n over 2 times the Frobenius norm, the sum of the squares of the entries, the Frobenius norm squared of the overlap matrix. Okay? So that's just 2 lines. Yeah?
So if the partitions are not balanced, their contribution is actually little o of exponential little o of n, right? If they don't matter.
Yeah, I mean, you have to make a little argument here, and yeah. Do we really need to talk about that?
Okay. Later.
Great. Or if at all. All right. All right. So now we're going to change this expectation into an integral over all doubly stochastic matrices, all possible values of this overlap matrix. And the question then is, how many pairs of partitions have a particular overlap matrix? And that is this thing I will call the entropy of zeta, where that's simply the average entropy of a row of zeta. Recall that zeta is doubly stochastic, so each row is a probability distribution. And then there's a factor of log k, because we're averaging over essentially k to the n squared partitions, ignoring the sub-exponential terms coming from whether they're balanced or not. And then we have this lambda squared d over 2 times the Frobenius norm minus 1. Okay. All right. Good. Well, so this is a lovely integral. How do we want to how do we want to compute this? And let's see, what did we want anyway? What we want is for this whole thing to be order 1. This is our second moment. We want it to be bounded. All right. So let's pause and look at this integral for a moment. Well, suppose that zeta was the matrix of where 1 over k everywhere, the matrix of all 1s divided by k. In other words, suppose that sigma and tau, these two partitions into k groups, were completely uncorrelated with each other. Okay, suppose those were the pairs which contributed the most to this integral. Well, then everything would be great, because this entropy would be log k, and that would cancel this, and the Frobenius norm squared of this matrix is 1, so the whole thing would be 0, and this would be little o of 1. And yes, the polynomial terms miraculously work out when you do this. Okay. So what we would like is for this whole function, we want this to be maximized by zeta equals this flat matrix. And lots of you know this. The point is that the second moment works when the pairs of objects that we're counting that contribute most to the second moment act like independently chosen pairs. If it's maximized somewhere else, then there are all these correlations. Correlations mean variance. Variance means the second moment method fails. Then this would be something exponentially large. All right, well, so when we saw this, we had a glimmer of recognition, because this is almost exactly the same as what you get when you try to prove a second moment lower bound on the k-colorability threshold in random graphs. And when you first look at this problem, you say, okay, well, I know that maximizing a function over all doubly stochastic matrices, that's a high-dimensional space, but give me a break. Surely this maximum is achieved by something in a one-parameter family, rather like that one-parameter family, something times the identity plus 1 minus that something times the flat matrix. I mean, come on. So, I mean, the trade-off, of course, is that the flat matrix maximizes the entropy, but the identity matrix maximizes the Frobenius norm. Every several years, I spend several months trying to prove this. Put me out of my misery. Prove that if we fix the Frobenius norm of a doubly stochastic matrix, then the entropy of its rows is maximized by something in this one-parameter family, or vice versa. Because then this would be a one-dimensional calculus problem, and lots of things would be easier. Well, if you don't feel like doing that, instead, you can do what Achleoptis and Lior did, which is they said, all right, this problem seems kind of surprisingly hard. I'm happy to tell you my sufferings if you want to hear about them. So instead they said, let's get an upper bound on this by solving a relaxed problem. Let's maximize over all singly stochastic matrices instead of doubly stochastic ones. So now, of course, we'd have independent constraints on the rows. They still needed lots of quite clever arguments, but it is easier. And what they showed is that this works as long as this coefficient here, lambda squared d, is less than or equal to twice log k minus 1 over k minus 1. And in case you think that they gave up too much by relaxing to singly stochastic matrices, the most you could gain by really doing it, if this was true, is changing these k minus 1s to k's. So it turns out this is actually pretty tight when k is large. So good. What we have proved now is a lower bound on the condensation threshold slash the information-theoretic detectability threshold of this. And why is this nice? Well, I neglected to tell you before where the easy hard threshold is. So this problem, I think, has a nice recent history. So in this paper by Dessel, and me and Lenka and Zde, we conjectured that this problem got easy when this crossed 1, okay, which is also the Keston-Stigum bound, or the bound for robust reconstruction on trees. This was then proved by Nacelle, Neiman, and Sly for K groups. Just recently for larger numbers of groups, it was, I guess he only has 4 letters anyway, so by Abbey and Sandon. The negative side for 2 groups that below there you can't do anything was by Nacelle, Neiman, Sly, and independently Massoulier. There's also a spectral method based on this thing called the non-backtracking matrix, which was written by lots of us and then was proved just this past year by Bordenov and Lalarge and Massoulier. Interesting that it takes more people to conjecture things than to prove them. I think that's because you need to do some experiments. Anyway, so for 2 groups, everything is known now, but what this shows for, at least for, okay, all right. This is a lower bound. I'm not going to show you the upper bound because it's too easy. So the upper bound is just a first moment argument showing that above a certain point, with high probability, the only partitions that are roughly as good as you would expect the ground truth to be are in fact correlated with the ground truth. Okay, so that's an easier argument. And for a certain regime of lambda, it's within a constant of this. So you should view this as theta of log k over k. And so what does this show? It shows that for a sufficiently large number of groups, indeed, the information-theoretic threshold is below this Keston-Stigum bound where belief propagation and spectral algorithms work. I should mention that the upper bound part of this argument was also independently obtained by Abbey and Sandon, but not this lower bound. Good. So that's my time, but I just wanted to mention that you can carry out this whole thing as well for the clustering problem, which was one of the problems that Florent talked about today. So let me just define it, and then I'll end. So let's say that you have k clusters of m points in n dimensions, and this is this nice, we're interested in this nice sparse regime where m over n is some constant, okay? So some people like to call this the big data limit. So in many cases, big data is actually not very big per variable. Okay, so per coordinate, we actually have not so many points. And then, you know, these clusters are located at various vectors, which are, say, chosen randomly. And then for each point you choose randomly you choose a partition, sigma, to tell you which cluster each point belongs to, and then you add Gaussian noise to everything. And the interesting regime is where the Gaussian noise has variance 1 per coordinate. So the size of the noise vector is typically root n, but the separation between these clusters is only order 1. Okay, so the clusters overlap a lot. So analogous to the sparse block model, we have no hope of labeling every point correctly. We can only hope to do better than chance. And here we can again show that when there's a sufficiently large number of clusters, the information-theoretic threshold is strictly below the threshold at which spectral algorithms like PCA work. And that is the work. So this stuff with Jess and Joe and Praneeth just got accepted to Colt, and this stuff about clustering with Jess and Raman and Jiaming, I'm sure will be accepted somewhere wonderful. All right, thank you very much.
probably time for more questions.
This threshold where the algorithm works, is it where it fails, starts to not work, or starts to work?
Moving
Wait,
up.
can you discuss like what's going on?
So if this is bigger than 1, then belief propagation does better than chance. And we believe indeed it is optimal. But we don't quite know that yet, right? Anyway, but we strongly believe that in fact it is optimal, that nothing can achieve a higher accuracy, a higher fraction of nodes labeled correctly.
You mean algorithmically, or I thought you just showed that the log k over k thing is the information-theoretic.
Right. This is the information-theoretic threshold, but we don't have an algorithm. What we would do is exhaustive search. Look at all partitions.
No, but then I guess I'm not sure what you mean by it's optimal if it's. But I mean then.
Sorry. Right. Okay. Yes. Above this point, we think that belief propagation is Bayes optimal, that it achieves the highest accuracy, just as high an accuracy as you would get if you could magically sample the entire posterior. So below this point, and Florent showed us this as well, I mean, what's going on is that, okay, so for 2 groups, everything looks like this. Here's belief propagation, and below here nothing works, information theoretically. Okay, so that's what Massel, Newman, and Sly showed. For a larger number of groups, and larger here is like 5, what happens is when it's easy, belief propagation, starting with random initial messages, goes there, but it has a discontinuity, because what's really going on is then there's this regime where there are 2 competing fixed points. The one where everybody is equally likely to be in every group, and the one where you would stay near if you magically started at the ground truth. The problem is that this one has a very small basin of attraction. So in physical terms, there seems to be a free energy barrier between these 2 things. Then the condensation point is the point above which, if I actually showed you both of these fixed points, then as a good Bayesian, you would choose this one. Below this one, there's actually exponentially many other fixed points that aren't accurate, that look equally good. Okay, so that's the point where, yes, there are clusters, but they all look equally convincing. So it depends what you mean by belief propagation. If you had time to explore the exponentially large space, you would eventually find this fixed point as well. But if you start from random initial conditions, most of the time you won't see it.
Do we have time for another question? And on the other hand, we might have coffee. And let's thanks again Cris for